Welcome. And you're watching this video because you're interested in antifreeze. What are we going to be doing with antifreeze in the CTC 250 lab, right? I mean, antifreeze of all things? Well, the answer is yeah. Antifreeze is a very common material that is tested in a laboratory setting because every manufacturer of every car has their own standards of antifreeze that should be used in their vehicles, believe it or not, and these antifreeze samples need to be tested for multiple things. Now, we have a laboratory in Wilmington that actually does this. They're called SAS, Southern Analytical. And they're right off of 421, where the bypass hits. You'll probably see them if you ever go up to Eagle Island, which is that kind of produce section that sits over on 421, over on the right-hand side. Just keep on a-trucking, and up to the left, before or a little bit past the overpass, you will see SAS. And that's really a large part of what they do. So I want to talk to you a little bit about antifreeze. You know, what is antifreeze and why should we really pay attention to this? And what's inside of antifreeze that we should be monitoring and measuring to make sure that it's going to be okay? Well, first off, what's the purpose of antifreeze? So antifreeze, first and foremost, lowers the freezing point of water. I mean, that's why we call it antifreeze, okay? Yeah, go figure. The problem here is that we could use water in your engine coolant system. However, water at a low temperature, you're going to have to be really careful with it. And the reason is because this water will expand. And as it expands, well, this could really do some damage to the internal workings of your car. Right? Hoses could bust, pieces could bust out. This is something that we do not want to happen, all right? Because then you're not going to have a car to drive. So we have to make sure that water is not going to freeze and expand like an ice cube inside of your vehicle. And that's the purpose of antifreeze. So antifreeze normally is a 50-50 mix. It's a 50% antifreeze and 50% water for the most part. People make it a different way. Different solutions are out there, but a 50-50 mix is typically the easiest and the most common. The other thing is that salts. Salts can also be brought into the picture. Salts do a wonderful job to do what we call de-ice, right? And if something can de-ice, then all of a sudden, why can't I use salt water in order to put into my engine? And the answer is you could, right? If you take water and you salt it the proper way, this will lower the freezing point of water. So it will have a harder time to freeze. That's why they put salt on the roads in the wintertime, people, right? It's to prevent them from freezing and icing over on you. The issue, though, is that if we just do salt water, the salts that are contained in that water sample would actually corrode all of the metal pieces that's inside your vehicle. That's also bad news, right? So you don't want water in your coolant system. You don't want salt water in your coolant system. So therefore, we have made this product, and this product is called Antifreeze. And Antifreeze makes sure that water will not freeze at the normal freezing temperature of 32 degrees or 0 degrees Celsius. And it also helps ensure that salts are not present. Most of the antifreeze samples will tolerate temperatures of negative 34 Fahrenheit or negative 37 Celsius. Now, we are a Fahrenheit bunch of people, right? So I don't necessarily think that we live in an area that ever gets negative 34. We barely even get into the 30s. However, if I lived in places like Canada or in the Northeast or maybe in the states like North Dakota, South Dakota, those places get a little cold too. These are the areas that I would kind of want to pay attention to the temperature of my vehicle. And I want to make sure that that liquid does not freeze inside of my vehicle. People also put corrosion inhibitors in. And corrosion inhibitors do just that. They inhibit the corrosion. Well, what's going to corrode? Well, these are the metal pieces that you're going to find inside of your vehicle. All right. Any metal that liquid comes in contact with, if you are not careful and if the antifreeze is not made the proper way, then this could bring in some contamination. And this contamination could slowly eat the metal away. And these metal pieces are made of really pretty much everything: aluminum, iron, copper, brass. I mean, everything you might find inside of the internal workings of your vehicle. So corrosion inhibitors are often added, and this helps prevent that slow breakdown of a metal. And all of this together, right? Fresh antifreeze with corrosion inhibitors, it's not going to last forever. So this is why some of the car manufacturers will tell you to do a antifreeze flush or engine coolant flush every 2 to 3 years, sometimes every 5 years, depending on what your antifreeze is and what kind of manufacturer your car is. But more than not, it's around 2 to 3 years of an antifreeze or engine coolant flush. So what exactly is antifreeze? What's the compound inside of it? We'll get there. But I also want to talk about another thing about antifreeze that a lot of people just don't really know. And this is, yes, antifreeze is used to make sure that your liquids do not freeze inside of your vehicle. However, antifreeze will also help your car engine heat a little bit hotter. So water normally boils at 100 degrees Celsius or 212 degrees Fahrenheit. And when we put antifreeze inside of our vehicle, that mixture actually changes the property of really just normal typical water. It increases the boiling point of water. So our cars typically run a little bit hotter than 212, and most antifreeze will actually allow that temperature to go up to 265. So this way, this liquid that we are pouring into our vehicles, it will not evaporate or turn into a gas and try to escape or explode anything internal. So antifreeze kind of does the best on both sides of the house. It lowers the boiling point for water so it doesn't freeze on us, and it increases the boiling point of water so it doesn't begin to boil away on us when we get behind our steering wheel and drive to the school or to work. So what exactly is antifreeze? We know that it has some water in it, but what is the other component? Well, that other component is something that we call ethylene glycol. Now, there's a couple of different additives that can be put inside of antifreeze. Propylene glycol is the other option, but ethylene glycol is going to be the most common. You know, back in the early days when antifreeze was first made, we first started off with just methanol, right? That's all that we were using. The problem, though, is that methanol has a very low boiling point. And if the system is not sealed, that methanol is going to escape and it's going to evaporate. And then before you know it, we're running a vehicle with no engine coolant at all in it, and things are beginning to overheat. And we'll be finding ourselves on the side of the road if that happens. The other thing about methanol is that it does corrode metals. And this is something that we did not want, right? We don't want to put a liquid in so we can run our car for a little bit, but know at the same time that that liquid is eating our metals away on the inside. So methanol was not used for a very long amount of time. It was finally replaced with ethylene glycol, and ethylene glycol can oxidize, and it can change, and it can decompose. And what it can decompose in is a couple of different acids down here at the very bottom. So you're probably looking at this right now, and the structure of ethylene glycol is up here at the top, by the way, to the top right-hand side. Ethylene, ethyl is 2 carbons, so there's 1 carbon, and there's the second carbon. Glycol, OL ending, is alcohol. So here is your first alcohol, and there's your second alcohol. So you're looking at all of the things that are on the screen right now, and you're saying, well, how does this really involve ion chromatography? This doesn't really make any sense at all, right? Here, I don't really see full ions. I don't really really see fully negative and fully positive things. Ethylene glycol is not an anion or a cation. Methanol is not a cation or an anion. And then what ethylene glycol breaks down into: formic acid, oxalic acid, glycolic acid, acetic acid. All of those, they are not anions or cations. Those are acids. So how on earth are we getting charges out of this substance that we can run on the ion chromatograph system? Well, the answer here is that we're not really monitoring ethylene glycol. We're monitoring other things that are inside of the antifreeze. So we'll eventually get there, all right? So ethylene glycol can come to us in a couple of different forms as far as antifreeze goes. They will start to add things inside of the ethylene glycol mixture other than water, of course. We've talked about some of these additives. And propylene glycol was also another substance that could be used in antifreeze. The reason that we started to make a change is that ethylene glycol metabolizes into calcium oxalate. All right, so calcium oxalate's here, and calcium oxalate are otherwise known as kidney stones. Okay. So what begins to happen here is that ethylene glycol is very poisonous, and it's very sweet tasting, and a lot of people really like the flavor of ethylene glycol, and a lot of animals love the flavor of ethylene glycol. It's like a sugar water, right? So if you add some ethylene glycol into a liquid and you have that person drink that liquid, basically what happens here is that person would never pick it up. That person would never take a sip and go, ooh, that's weird. But that person's body would react to the ethylene glycol, and calcium oxalate would immediately form. And they begin to have kidney failure. Not only that, but it can also crystallize in the brain as well. So we have complications as far as health is concerned. If your car is very leaky with antifreeze and it goes onto the pavement of a parking lot or a driveway, and you have some kind of house cats around or some outside dogs or animals that kind of come and go, those animals typically gravitate toward the ethylene glycol. It tastes very sweet to them as well, and then they will end up dying with it too, just basically due to kidney and brain malfunction. And if it is kidney related, it is kidney stone related. It can just completely jams up everything that needs to come out. So propylene glycol was used as an alternative to the antifreeze mixture. And this is out on the market. This is getting used now. But again, this just really depends on the car manufacturer and what they recommend you putting into your own vehicle, because antifreezes are different depending on what they are. The antifreeze laboratory experimentation and test, they are formally inside of your government under ASTM D3306 and ASTM D6210. The reason I'm pointing these out is because these are basically regulations that are set forth onto antifreeze products, and these are the testing methods that come along with the antifreeze. So the D3306 is going to be the glycol-based engine coolants. And notice it doesn't say ethylene glycol. It just says glycol, right? So it's glycol-based engine coolants for automotive and light-duty engines, which is probably what you drive. And then the D6210 is really the testing procedure for the glycol-based engine coolants for heavy-duty engines. And this is probably something that you are not driving. This would be something more of the heavier type of vehicles like rigs and that type of thing that you might see on the interstate. However, within this category, we do have different classifications of antifreeze, and there's different types of coolants, and they're going to be ranked 1 through 6. And what you're going to find is that number 1 and number 2 coolant types, one's going to be ethylene glycol-based concentrate, and 2 is the propylene glycol-based concentrate. So again, different types of samples that might be given to a laboratory to test, and we can kind of categorize them based on what we know about them in the very beginning. Notice it doesn't go straight to 3. I'll come back to that one in a minute. But if you do go straight to 3, this is ethylene glycol that's pre-diluted with water at half concentration. And then number 4 is the propylene glycol, which is pre-diluted to 50%, which means 50% propylene glycol, 50% water, the same as the ethylene glycol from up above. So there's 1, 2, 3, and 4. 1 and 2, ethylene and propylene glycol concentrates. 3 and 4, ethylene and propylene glycol diluted at 50%. And then we get 5 and 6. 5 is ethylene glycol that contains a little bit of glycerin. All right. Glycerin is a very slippery, oily type of material that you might find in a common lubricant, let's say. And then number 6 is the ethylene glycol with glycerin diluted at 50%. So there is 1 through 6 right there. Okay, so different classifications, different types of coolants. Yes, one antifreeze is different than the others, and it really does depend on what car that you have on which antifreeze to purchase. So always keep that in mind if you're going to do this on your own. pHs of antifreeze are also regulated. They're also tested with a common testing procedure. This also comes out of ASTM D3306, and it says that the antifreeze should be testing between 7.5 and 11. So low pH values, which mean more acidic, are going to start to eat your metals away, and this is something that you do not want. Notice on the screen it says pH equation. What is the pH equation? Well, I hope that you know. The pH equation is negative log of the hydrogen concentration. That is the pH equation. So basically what happens is that if I want to calculate pH, I take the negative log of the hydrogen content. And the hydrogen content is going to be in the factor of molarity. So I'm not going to ask you to ever really solve for a pH equation here in this laboratory in particular, but that is the pH equation just as a quick review. Here's a pH scale. Again, we're saying 7.5, so that's going to be about here to 11, and it's going to be within this range. So antifreeze is a very basic, or another word for that, alkaline substance. We are working on the basic side, and the basic side are going to be detergents and baking soda, borax, antacids, milk of magnesia, seawater, eggs. All of those are in the range of where a normal antifreeze solution would be. So it is a basic solution. It is not acidic. If we do go into the acidic territory, and maybe over time you have old engine coolant or decomposed engine coolant, it just changes over time while it's there. This does lead to corrosion, and this acid content will start to eat away your metals, and then before you know it, you're going to have problems other than just an antifreeze flush, because there's going to be pieces and parts. It's going to cost a lot of money in order to get those replaced and fixed. We can talk about freeze points as well. Antifreeze 50-50 should have a freeze point of about negative 33, right? So keep this in mind when the temperatures get cold outside. A 50-50 mix, which is the freeze point of or antifreeze, is going to be around a negative 33. So you can go as cold as that before this thing really begins to ice cube on you in your vehicle. Freeze point can be determined in a laboratory. The only thing that you have to do is just put the sample into a freezer, and then you just measure the temperature when it freezes. There are automated contraptions and instrumentation that will do this for you, or you can simply put it into the freezer and check on it every 5 minutes or so, and just keep looking at the temperature of a thermometer. It's as simple as that. It doesn't need to be more complicated, but there is a little bit of automation involved nowadays if you have to do this on your own. Here on the screen is probably going to make your general chemistry teacher very happy. This over here to the left-hand side is called a phase diagram. And you probably saw the phase diagrams in maybe Chem 152. And the phase diagram, the whole purpose of this is just to let you know that many of the substances that you work with do have a solid, liquid, and a gas state of matter, right? That's all that the phase diagrams are doing. So the solid is basically here on this side of the graph, okay? And the liquids are basically going to be here in between these two solid lines. We're only looking at the solid lines right now, okay? And then the vapor is going to be here. So we're only looking at the solid lines, and it's everything that's below. That's how we interpret this line. So if you look at the solid line, it always makes a Y for the most part. So there's your first solid, and there's your second solid line, and then here's your third solid line. This is a phase diagram. It separates the three phases from each other, okay? Well, when we talk about freezing point depression, what we basically are referring to is that we can add things into a liquid, and that liquid's boiling point, that liquid's melting point will begin to change. This junction right here in the center, where all three come into an existence, this is called the triple point, because that's kind of where a solid, liquid, and gas all kind of come at one point in time. And then if I go over here to the left, I'm now a solid. If I go a little bit above, I'm now in the liquid. And if I go a little bit to the right or down below, this is my gas phase for the most part. So if we add a salt, or if we add another liquid, like in the case of the antifreeze mixture, ethylene glycol and water, then these boiling points and melting points begin to change on us. And what you're seeing in the diagram is this dashed line. So you can see the dashed line kind of mimic what was here to the right-hand side of it. And here's a dashed line that's below the solid line up here. And then this phase diagram begins to change a little bit. And what you're seeing on the screen is this circle area here at the top and here at the bottom that they're going to call change of T. And that's the change of temperature. Basically what that means is that water typically froze at 0 degrees Celsius. So if we added this thing inside of water and the melting point and boiling point lowered, what is that new temperature? And the difference is what we call change of T. Again, nothing really that you have to do as far as that's concerned with this particular lab, but it is a good time to kind of review a phase diagram and really what it means and what kind of information you can take away from it. The information that you take away: what is my boiling point, what is my temperature, what is my pressure, and then what phase of matter am I working with if that's the case. The problem, though, is that a lot of people think that the more antifreeze that you add in, the lower the temperature is going to go, and that's not necessarily the case. What begins to happen is if you look at the graph here on the screen, up here at the top left-hand side, this is going to be the freezing point of water with no antifreeze added into it at all. And then as you add antifreeze inside of this solution, what you see is that the antifreeze will begin to plummet and lower and lower and lower the freezing point of water to a maximum. And this max, or kind of where it bottoms out, is going to be a little bit below -50. And this is going to happen around 60 to 70, we're going to say 75% or 65% antifreeze. Then after this point, what begins to happen is that antifreeze really, those properties kind of take over, and now there's less and less and less of water. And what you see is that the freezing point begins to increase because of that. So there is kind of a proper Goldilocks area with antifreeze, and that's happening around 65. And if you go more than 65%, then you're actually increasing the temperature of the antifreeze on when it does freeze on you. So for that reason, we often tell people to do a 50-50 split, and you're going to be working here. And the reason for that is we know the general consumer is not going to measure out very well. So you are probably going to be in a garage and you're going to eyeball things and you're going to say, well, let's just quickly do this. And if we give you 50, if you go a little bit over, then that's going to be okay. You're still going to have even a better antifreeze if that's the case. And if you go a little bit below, then that's going to be okay too, because you're still going to be in the -30s. So this is a typical temperature that we would always see people kind of live in, the -30 to the -50 degree in the cold winter months, and 50 was chosen for that reason. So 50% is not the best ratio. 65% is the best ratio for antifreeze. But because we know you're going to eyeball it, we're going to say 50. That way you can go a little bit below or a little bit above, and you still get a pretty good product depending on what you got. Now, again, I told you, antifreeze, it really doesn't carry any positive or negatives at this point. However, some of the positives and negatives are measured in an antifreeze sample, and one of them is going to be chloride. So this ASTM method, D3306, states that the maximum amount of chloride in an engine coolant, which is antifreeze, should be 25 part per million. All right. So chloride is going to be, of course, Cl-, carries a -1 charge. We do not want to see chloride in an antifreeze sample. If chloride is found in an antifreeze sample, it needs to be less than 25 ppm. If there is chloride present, what can happen here is that it will start to eat away the aluminum components of your vehicle. That's the problem. So antifreeze samples are typically sent out to laboratories for testing, and one of the things that we test for is pH, of course. One of the things that we test for is also chloride level, and that chloride level should be 25 or lower. If it's higher than 25 and you put this into your vehicle, it will begin to eat away your engine, and we don't want that. And in particular, it targets all of the aluminum components. We're also going to look for another anion, because that's an anion, right? It's negative. And the other anion is sulfate, and sulfate's SO4, -2. ASTM D3306 also states that antifreeze should have less than 50 part per million sulfate. In a new engine coolant, if they're selling it to you as a consumer, chloride and sulfate are targeted, and chloride's 25 and sulfate's 50. If you do find sulfate in an antifreeze sample, it's going to start to scale up and it's going to corrode your metals. Scale basically means it's going to start clogging the tubing and the pipes. You know, think of arteries and think of plaque. As the plaque builds up over and over, you're going to have a heart attack. The same thing happens inside of a vehicle. As the sulfate builds up and up, this scale is going to start to build up, and then sooner or later it could block the flow. And then you're going to have a heart attack maybe when you pull over on the side of the road and you can't get to where you're going because your car just broke down. These are not the only ions, though. There are other ions as well. Some of these other ions are things like nitrite, which are NO2s, and nitrates, which are NO3s, and then phosphates, which are PO4s. We're not really going to measure these, though, and the reason is because a lot of times these are added because they're good. The nitrite typically is added in to help prevent corrosion. The nitrates are typically added in to prevent corrosion due to aluminum. Phosphate is typically added in to prevent corrosion for iron and steel. And phosphate is also a very good buffer to control the pH of the antifreeze samples. So when we begin to analyze the antifreeze samples in the lab, there is a chance that we're going to see these other things pop up. These other ions or other peaks could show up and they could be present. And the nitrites and the nitrates and the phosphates could all be there, and we could see them. However, they're actually good if they are there. These are not really our number one concern. Our number one concern is really the sulfates and the chlorides. Those are the ones that's going to eat away. Those are the ones that's going to ruin the internals of the vehicle, and those are the ones that we want to keep an eye on. So, ASTM D3306 specifically states these are two of the things that you should report on and that you should measure. So here's the laboratory paper, really paper, one sheet, that's it, that you need to print off and bring to the lab when you're ready to do the lab. And what will happen is that up here in the very first block is the standard preparation. And more than likely, these standards are already going to be made for you. We've made these from our stock. We've already ran them in the instrument. That will save you some time. That will save you some trouble of making your own standards. But the standard preparation is up here at the very top. So the standard is what we would call a mixed standard. And a mixed standard is basically a volumetric flask that has been made, and this flask has chloride in it, and it also has sulfate in it. And we have diluted up to the line. We know the concentration of each one of these, right? And let's say that this represents flask number 1. So in that one flask, there's 0.25 part per million chloride and 0.5 part per million sulfate. And then we make another flask and have both chloride and sulfate in it at that level. Then we make another flask and have chloride and sulfate at that level. And we make a fourth flask and we have chloride and sulfate at that level in total. These are already probably made for you. They've already been ran. Just double check with us before you start the lab to make sure. If not, here is the target concentrations that you will have to make. Sample preparation, very easy. The only thing that you have to do is obtain the antifreeze sample, and you make a 1 to 50 dilution of it. Basically what that means is that you're going to take a volumetric flask, and you're going to add 1 ml of antifreeze to that 50 ml volumetric, and then you take it up to the line at the mark. That's all that you have to do. Give it a good shake, give it a good mix, and then we want to make sure that we filter it through a micron filter or a membrane filter, 0.45 syringe filter. All right, they're all basically talking about the same thing. Again, that filtration process is very important. If you do not filter, it gums up our instrument and it stops everyone's analysis. And if you are found for your sample to do that, and we know that you did not filter your samples the proper way, you will get an automatic failure. So make sure that you filter them appropriately. Now, depending on what we want, we could bring in different antifreezes and we could have you compare them, or we could have you to replicate that maybe 2 more times to get a really good average, but you'll know that when you actually do the lab. So just be prepared to make more than 1 sample prep. That's really all that means. The QC sample is going to be made by the lab. This is a sample of known chloride and sulfate to us, but not to you. So you're going to take the QC sample, you will dilute it just like you did the antifreeze, and you will filter it just as you did the antifreeze, and you will run it along your antifreeze samples. You'll report those concentrations back along with the antifreeze concentrations that you've discovered and determined, and we'll see if you are close. The instrumentation that you're going to be using is the Metrome IC system, and of course it is the anion version of the Metrome IC system. So we want to make sure that we are picking out the right instrument. We're picking out the anion setup, not the cation setup. So hopefully when you get ready to run these samples and load these samples up on the piece of equipment, these samples will be loaded, these samples will be analyzed on the right machine, not the wrong one, because then you're going to have to do it all over again if it is. Finally, you will see a spreadsheet template available to you in Blackboard. When you open it up, this is what it's going to look like. Really, all the work's done for you. It's very similar to all the others. Only thing you have to do is type in your areas for your chloride over here to the left, type in your areas for the sulfate over here to the left, and use those concentrations and those areas to generate a calibration curve for chloride, which will be at the top, and a calibration curve for sulfate down here at the bottom. The information for your regression lines and your coefficients will go into the respective boxes, so that's where you'll key in that information so we can double check it. And then finally, down here at the bottom, you're going to see a sample information for chloride section and one for sulfate section. So the name of the sample will go here. Maybe it's ABC 123, who knows. The area for the chloride peak will go into that box. You'll use the calibration curve to solve for your concentrations. Remember, this was diluted a 1 to 50, so you're going to have to backtrack and calculate the concentration of the original before the dilution began. So this is the concentration of the diluted one that was made from a 1 to 50 dilution. Do you know how to go back and calculate the undiluted version? And then finally, does the sample pass? And we've already talked about the cutoff values, part per million wise for chloride and part per million wise for sulfate. You do something very similar to the sulfate down here below. Areas for the sulfate peak. What were the parts per million of sulfate in the samples? That was a 1 to 50 dilution, so correct for that factor. And does it pass the criteria set forth in the ASTM method? Then down at the bottom, you're going to see quality control information for chloride and sulfate. Each one of those will have its own area. You'll calculate part per million. You'll calculate the undiluted part per million because that was also diluted 1 to 50. And then that will give you an actual concentration. Well, we will tell you what the actual concentration is. You'll key that into those blocks. Compare that to your undiluted concentration that you just solved for, and that's how you'll calculate an error for your data. So the template will be up. You're more than welcome to use that or use your own. That's really up to you. Finally, the last thing that I'll say is that when you go into Advanced Auto Parts or you go into an auto supply store like AutoZone and you begin to purchase antifreeze, please keep in mind that antifreeze really isn't meant to be a universal one-size-fits-all application. This is just a chart that basically says, listen, you know, depending on the year of the vehicle that you have, you could have to use different antifreeze brands. I mean, that's why there's so many different choices that are out there. So you want to pay attention to the particular year, and you also want to pay attention to the model of your vehicle. So for instance, if it's American made, or if it's European made, or if it's Asian made. So Toyotas and Hondas, Mazdas might be a little bit different than your BMWs and your Volvos and your Mercedes. So keep that in mind. Do not go into an auto store and get whatever kind of antifreeze you see on the shelf thinking that it's going to work for your model. Pour it in only to figure out a little bit later that it's not going to work for you. All right? So that's what I want to say about the antifreeze lab, right? That's as simple as it is. We're going to dilute antifreeze down to 1 to 50. We're going to run them on the IC instrument. We're going to look for chloride and sulfite levels, and then we're going to see if they pass yes or no. And that's really all that there is to it. Also keep in mind that we could easily do this before and after the fact. However, we're going to bring fresh antifreeze in for you to test, not used antifreeze. But that would be something kind of interesting to compare the differences between a original antifreeze in the jug compared to the sample 2 years later after you begin to use it. So have fun with the antifreeze lab. Just make sure that you clean up after yourselves. Make sure that you wash the glass really, really well. We probably will not tell you to dump the antifreeze down the sink, so we'll have a disposal jug for that. Just make sure that you dispose and that you handle this product a very particular type of way. This is something that we do not want to dump down the sink due to the environmental concerns that's associated with the antifreeze or the ethylene glycol mixture. All right, so have fun. If you have any questions, let me know. And if not, I'll see you at the IC instrument with your antifreeze samples getting ready to run them.